Okay, hi. We are going through the Unit 3 practice written test. As you can see it here, I'm going to talk about all these questions while I do them on the nicest day of the spring so far, and you're probably outside. My friends and family are outside, but let's get into this instead. This is probably more fun. All right, so it tells you what kind of questions you can expect to see. The first question is going to be a balancing problem, just like these, already written out for you. You just have to crisscross and balance it. I'll crisscross one to refresh your memory, but other than that, you should probably know how to crisscross at this point. So if you have magnesium bromide, you're saying that magnesium is +2 and bromine is -1. So when you crisscross them, you get this. You're also a lot of sneaky sevens on these, so be aware of that. Like chlorine gas is a sneaky 7, so Cl2. And it reacts to produce, so there's your arrow, magnesium chloride and liquid bromine. So magnesium chloride, again, magnesium is +2 and bromine is -1. And so you get this. And then, of course, bromine's also a sneaky 7, so get that 2 there. And then, of course, we have to balance these, but it looks like it's already balanced. Two chlorines, 2 bromines, and 2 magnesiums. So there is an example of one of them with the crisscrossing. Now I'll go a little bit faster because you should know how to crisscross. So sodium chloride and sulfuric acid, NaCl. Sulfuric acid is hydrogen sulfate, so H2SO4. And then you make sodium sulfate, which is this guy. And you also make hydrochloric acid, which is that guy. Then you can balance it by putting the 2s and whatever else you need in place. So 2 sodiums, 2 chlorines, 2 chlorines, 2 H's, 2 H's, and 1 sulfate. And we're all set there. On to the next one. Aluminum reacts with solid sulfur when heated to create solid aluminum sulfide. So aluminum is just aluminum. Reacts with, there's our plus side, solid sulfur. Oh, okay, easy. And when heated, not necessary. We don't need to show what that is. To make solid aluminum sulfide, aluminum +3, sulfur -2. So when you crisscross, you get that, and easy to balance. I don't believe on the test it says to justify or that why this is a composition reaction. But this is a composition reaction because you're taking 2 things and you're making one thing, 2 elements making one thing. That's the definition of a composition or synthesis reaction. Next, we got hexane, which is C6H14, and it's burning in oxygen, which is oxygen, sneaky 7, and it produces water and carbon dioxide gas. So you know those. And this is a combustion reaction because it reacts with oxygen to make water and carbon dioxide, and you should balance them alphabetically. So 6 carbons, 14 hydrogens, 7 times 2 is 14, and then we're going to get into an odd number situation here, but you've got 6 oxygens plus the 14 on the right-hand side. This is not an odd situation, I guess, because 6 plus 14, of course, is 20, and so you can put a 10 here to balance it. And we can maybe even get real granular and move this over. Do you think this is worth my time? I'm doing it anyway. This is a mistake. I immediately regret my decision. Oh, I made it worse somehow. This is not good. Anyway, so there is your balance reaction for combustion. You've got hexane reacting with oxygen to make carbon dioxide and water. Ammonium nitrite. Ammonium is NH4 plus and nitrite's NO2. So NH4, NO2, and it makes nitrogen and water. Nitrogen is a sneaky 7. Water is water. And when you're done with those, this is a decomposition reaction because you take one thing and break it apart into some pieces. And if we were going to balance it, what should we do? I guess we'll do nitrogen first. No, nitrogen's already set. Then we have 4 hydrogens. So we do this and put a 2 here to give ourselves 4 hydrogens, which also has 2 oxygens and 2 oxygens already. So I believe that is balanced. All right, we just took a quiz like the next question. So number 2 will be something like this, which is is this the same one we had in the quiz? That'd be kind of funny if it was. I don't remember. And so we're going to do... This was the same one we had in the quiz. Maybe I can skip this one, but I'll do it quick for you in case you want to have the answers for it or show how to do it. First is balance in the reaction. I'll do that right here. For A, we've got Al2S3, we've got water, we've got aluminum hydroxide, and hydrogen sulfide. And I'm gonna write my water this way because I think it's easier. And so when we balance it, we would say that we need to have, let's see, 2 of these guys gives us 6 H's, 3 H's there, and I think that's all we need. So now it's balanced. That was A. B, determine the limiting reaction. So in determining the limiting reactant, we're going to take both of our amounts, 316 grams of aluminum sulfide, and we're also going to take 493 grams of water, and we're going to convert them both into moles. Molar mass of aluminum sulfide, we all know 27 times 2 plus 32 times 3 is 150. And the molar mass of water is 18. And we're going to get 2 numbers. Let's see, 316 by 150 is 2.11. And 493 divided by 18 is 27.3839. And if you want to find the limiter, you would divide them by the coefficients that are in the problem. So it's 1 for aluminum sulfate and 6 for water. So divide this by 6, divide this by 1. The question is 27.39 divided by 6 less than 2.11? And the answer is no. This is 4.56, which is not smaller. And so our limiter is aluminum sulfide. Make sure that you mark that well when we take the test. All right, so then we can calculate the amount of hydrogen sulfide gas that was produced. We'll write it right down here for C. Amount of hydrogen sulfide gas. Well, now we know that the limiter is 2.1. So you take your 2.11 moles of aluminum sulfide from part B. And we're going to use the mole ratio to go over to the one that doesn't run out. Sorry, no, we're not going to that. We're going to hydrogen sulfide. So it looks like it is a 1 aluminum sulfide for every 3 hydrogen sulfide ratio. And we want our answer in grams. So we keep going. We put the molar mass of hydrogen sulfide there, which is 34 grams per mole from the periodic table. And we take 2.11 times 3 times 34. Let's see if I didn't do that right. And I got 215.22. And that is what we call our theoretical yield. If everything went perfect, that's how much we make. But that's not exactly the case, which we'll find out in part E. So let's go to part D. And in part D, we're going to do, to figure out what mass of excess remains, we're going to take the one that runs out first and convert it to the one that does not run out or has not run out. What won't run out, that's the water. So we take our 2.11 moles of aluminum sulfide and we convert it to water, and you can see, ooh, that's not good. I should probably move this up. There we go. And then we can see that it is a 1 to 6 ratio. So for every 1 aluminum sulfide, we make or use 6 waters. And we want to know also how many grams that is. And so we do that as well. And we're going to put the molar mass of water on top, which is 18 grams per mole. So you take your 2.11 times 6 times 18, and you get 227.88. But that's not the answer because we want to know how much is left over. This is how much is used. So back to the problem. Actually, just above here in previous, this is, no, actually the problem, you're right. So 493 grams of water is what we started with. So we're going to subtract them, 493 minus the 227.88 to find out what is left over. And we will find out that you use 265.12 grams of water left over. Oh, and where are we going to put E? What if you really made, oh, that's a small one. 200 grams of hydrogen sulfide, calculate the percent yield. So we were supposed to make right here 215 grams of hydrogen sulfide, but we actually made 200 instead. So to find the percent yield, I'm just going to do E right here. You're going to have to live with that. Just take the number that they gave you, which is the 200, our actual yield, divided by the number we were supposed to make, which is 215.222. Multiply that by 100 to get your convert to a percent, and you get 200 divided by 215.22, and I got 92.9%. So fun. There you go. Big, old stoichiometry limiting reactant problem. All right, next we're on to an empirical formula problem, empirical and molecular formula. So these problems, we did a couple from the book, and we'll do this one right down here. We're going to say, first thing you do is you convert all your percents to grams, and I say convert, but I mean just literally change them. So it's 48 grams of carbon and 8 grams of something else. Hydrogen, 28 grams of nitrogen, and, wish I could eat. You know what, we're going to do it. Let's move it right here so we can squeeze in our oxygen, 16 grams of oxygen. Then we're going to convert them all into moles by dividing by their molar masses. So we're going to do all of this work right here, and it's going to be super sloppy. 1 on top for all of them. It's 12 here for hydrogen or oxygen. Nope, that's carbon. 1 for hydrogen, nitrogen's 14, oxygen's 16. And you can see the setup we got here, 48 divided by 12, what's that, 4? 8 divided by 1 is 8. And 28 divided by 14 is 2, and 16 divided by 16 is 1. And then the last step of these is to divide them all by the smallest number, which is the 1. So you take them all divided by 1, and of course they just stay the same. So these become our little numbers in the empirical formula. So it would be 4, 8, 2, and 1, and that would be C4H8 N2O, 1 oxygen. And that is the empirical formula. So where it says determine the empirical formula, that's it. Now, if you want to know what the molecular formula is, you add up the molar mass of the empirical formula. So you take 4 times 12 plus 8 plus 2 nitrogens plus oxygen. So we add up all that up, 12 times 4 plus 8 plus 14 times 2 plus 16. You get 100. What a coincidence. It's crazy. So, and then our compound is 200 grams per mole. So you take the 200 that gave you this number, whatever that number happens to be in this problem is 200, and then divide it by 100, and you get a whole number. And then that's the number you multiply back into the empirical formula to find your molecular formula. So the molecular formula is just double that, C8H16N4O2. This is the empirical here, and this is the molecular formula here. Finally, we just got easy conversions. Okay, no stoichiometry here, no balance reaction, just converting. This will be all triangle. This will all be mole wheel problems for you. So you can use that. It's given to you getting Foldy on this test. In A, starting with 196 grams of sulfuric acid, determine the moles. So 196 grams of sulfuric acid. That's not how it is. It's H2SO4. Molar mass of sulfuric acid is 98 grams per mole. So you get that from the periodic table. 196 divided by 98, I'm guessing that's 2, and so our answer is 2 moles of H2SO4. Next one, number of moles of oxygen. Well, if you know that you have 2 moles of H2SO4, and you can tell by the formula that that there are 4 oxygens in there. So you're just going to say for every 1 H2SO4, there are 4 O's. And so 2 times 4 is going to be 8 moles of oxygen atoms. You can do the same thing for hydrogen, for letter C. You can say we've got 2 moles of H2SO4. And this time we want to know the number of atoms. Last one wanted to know the number of moles. Moles of oxygen atoms. Okay, so now we always want to know the number of atoms, not moles, of hydrogen. And so for every one H2SO4, that's a 3, you have 2 hydrogen atoms, and sorry, you have 2 moles of hydrogen. That's would be better. I'm going to erase this one too. And then you're saying that for every 1 mole of anything, there are 6.02 times 10 to the 23rd of that thing. So that would be 4 times 6.02 times 10 to the 23rd, and you get 2.41 times 10 to the 24th. And the label for this one would be hydrogen atoms. And finally, molecules of sulfuric acid. We're just going to go with starting back at moles. So we've got 2 moles of H2SO4 from part A. And we're going to say for every 1 mole of anything, there are 6.02 times 10 to the 23rd of that thing. And so then this would equal 1.2 times 10 to the 24th molecules or formula units of H2SO4. All right, so no surprises on the written test. You're going to be looking at something that looks just like this. We've got to review writing reactions, or I guess transcribing them. They're already written for you. That's crisscrossing. Remember your sneaky sevens, balancing. And then you've got a big, long stoichiometry problem with a limiting reactant and a percent yield, and also how much is left over. You've got an empirical molecular formula problem, which has always the same steps. And then finally, you've got some easier, let's call them easier, straight up